Modern smartphones and tablets use displays covered by thin sheets of strengthened glass, enabling weight reduction and improved scratch resistance. The high strength is achieved by generating high tensions inside the glass sheet. Fabricating the curved contours of these covers without chipping, burr and edge rounding requires sophisticated technologies like cutting with ultrafast laser pulses. High volume production requires high processing speeds, which is possible with powerful lasers only. Laser material processing using continuous wave lasers typically leads to a strong heat flow into the material, causing a large heat affected zone and significant melt flow. This limits the minimum feature size and the achievable quality severely. Nanosecond pulses allow reducing these thermal effects, but still lead to a significant melt generation. Therefore, to fabricate the most precise structures in transparent materials like glass, sapphire and diamond, typical pulse durations in the 100 femtosecond range are needed. The thin disc laser concept is based on a thin laser crystal. A thickness of a few tenths of a millimeter only allows for efficient axial heat extraction. This geometry drastically reduces the thermally induced optical effects observed for the usual transverse cooling and severely limiting the fundamental mode output power of rod lasers, including the existing titanium-doped sapphire lasers. Thus, the thin disc concept enables scaling the output power in fundamental mode operation into the multi-100 watt range. In a conventional thin disc laser, one face of the disc is cooled using an opaque heat sink. The cooled face is highly reflective coated for the pump light as well as for the laser beam to be amplified. The pump optic enables multiple passes of the pump light through the disc to achieve efficient absorption despite the low thickness of the disc. In most cases, between 16 and 32 passes are needed to absorb most of the pump light. The laser resonator is completed by arranging a partially reflective mirror opposite to the highly reflective laser disc. When pumping the laser, a laser beam builds up inside the resonator and a part of it is coupled out through the partially reflective mirror. Replacing the common ytterbium doped disc by a titanium doped sapphire disc allows generating ultrafast pulses with durations well below 100 femtoseconds at average powers exceeding 100 watts. Unfortunately, titanium-doped sapphire produces roughly 4 times more waste heat than the ytterbium-doped materials. Therefore, cooling a titanium sapphire disc from one side only severely limits the pump power density and thus the available gain. Cooling the disc from both sides dramatically improves the heat extraction, but in this case, transparent heat spreaders are required to pass the pump as well as the laser radiation. The only transparent material having sufficient thermal conductivity is diamond. The heat is extracted from the diamond heat spreaders using microchannel coolers. The assembly is clamped inside a holder. The pump optic has to be adapted to the transmissive laser disc setup. As before, the pump light passes several times through the laser disc to allow efficient absorption. The laser resonator consists of a rear mirror, several folding mirrors and an output coupler. Folding the resonator beam through the laser crystal several times increases the round-trip gain and leads to a resonator length of approximately 15 meters. Pumping this oscillator with continuous wave radiation yields continuous wave emission in the 100 watt range. When introducing a suitable mode locking device into the resonator, the laser will emit ultrafast pulses. A 15 meter long resonator leads to 10 MHz repetition rate, corresponding to pulse energies in the 10 microjoule range. For higher pulse energies, a chirped pulse amplification system pumped with nanosecond pulses at 20 kHz repetition rate will be demonstrated. The amplifier chain will be seeded by a low power femtosecond oscillator. To reduce the peak power, and thus the non-linearities in the amplifier stages, the pulses pass dispersive elements stretching their duration roughly 1000-fold. A conventional titanium sapphire regenerative amplifier increases the pulse energy from the nanojoule to the microjoule range. The pulses are further amplified in a titanium sapphire thin disc multipass amplifier. To achieve the required gain, the laser beam passes the thin disc several times under different angles. This approach avoids optical switches, which would limit scaling of pulse energy, average power and repetition rate. Finally, the pulses are recompressed to their initial duration by using a second set of dispersive elements. A pulse energy of 10 millijoules, corresponding to a peak power exceeding 100 gigawatts, is achieved at the output. The drilling of small holes in transparent materials like glass, sapphire or diamond will be investigated as an important potential material processing application of the high pulse energy femtosecond laser system developed in the project. Special beam shaping techniques allow generating so-called Bessel beams, which enable drilling of up to 0.5 mm deep holes with a single laser shot. These holes can be more than 20 times deeper than wide. The high repetition rate of the femtosecond laser system realized in the project will allow drilling of up to 20,000 high quality holes per second. The high repetition rate femtosecond laser system has a broad range of potential material processing applications, including precise surface structuring of various delicate materials, including thin film solar cells or organic LEDs. Volume structuring of transparent materials like containers for pharmaceuticals as protection against counterfeiting is another range of potential applications. Several selected applications will be investigated within the project. One focus will be on high-speed precision cutting of thin transparent substrates, for example made from glass or sapphire, which seems to be the most promising potential high-volume application. Employing the high-speed processing of transparent materials based on the high average power femtosecond laser systems developed within this project will lead to significant improvements in a broad range of applications, including the precise and cost-efficient cutting of advanced display cover glasses for smartphones and tablets. Kite Innovation supports the other partners and the coordinator regarding the management of the project, as well as regarding the exploitation, planning and dissemination of the results. The Institute FemtoST, which is part of CNRS, investigates material processing applications using a high-energy femtosecond amplifier system. Oxford Lasers investigates material processing applications using a high repetition rate femtosecond laser system. M² provides the enclosure, the active and passive stabilization, as well as the control electronics for the high repetition rate femtosecond laser system. Thales Optronique is responsible for the realization of the pulsed, pumped, high energy femtosecond amplifier systems. Element 6 provides the low loss single crystal diamond heat spreaders needed for cooling the laser crystals. The Institute IFSW at the University of Stuttgart is responsible for the project coordination and for the realization of the continuous wave pumped femtosecond laser systems.